So I think that what Sean did with showing how Burroughs-Wheeler can be applied to pattern matching is really awesome. But I'd like to point out that we're kind of back at an issue that we had when we were using the suffix tree, which is that he's been able to identify whether or not each pattern occurs in the genome using the Burroughs-Wheeler transform. But remember that the multiple pattern matching problem says we need to also find the positions. Okay, we need to know where it is that these pattern matches are happening. Okay, so the question then is, can we use Burroughs-Wheeler transform to reveal these positions? If we go back to our example, we know that ANA occurs 3 times in Panama bananas, but if we're using Burroughs-Wheeler and we just have the first and the last column, we don't know where it is that these pattern matches are occurring. So we'll use, to help us out, we're going to use a data structure called a suffix array. And this is going to hold the starting position of each suffix beginning a row. What do I mean by a suffix beginning a row? Well, each row of the Burroughs-Wheeler transform corresponds to a cyclic rotation of our original string. Okay, so if it's a cyclic rotation, then that means that you can walk to some point and reach the $, and that walking corresponds to a suffix. So the first row is just the $. So it's the suffix that ends the string, and that's in position 13, so we put a 13 on that row. The next row begins with A bananas, and the A bananas is in position 0, 1, 2, 3, 4, 5, starting position 5 of the original string, so we put a 5 in the second element of the suffix array. And we go through this. So AMA bananas is in position 3, and so on. So we get 1, 7, 9, and so on. So we reconstruct the entire suffix array this way. And so now we have this suffix array. So how is it helpful for us to find the matches? Well, if we look at the 3 occurrences of ANA that we found, we just say what are the corresponding elements of the suffix array. And this tells us that ANA occurs at positions 1, 7, and 9 of Panama bananas. So the suffix array values are 1, 7, and 9. And here is starting position 1, 7, and 9, which we saw before. The issue, though, is I know what Sean will say, which is how much memory is it that the suffix array took? And this is an issue. In fact, if you represent integers as using 4 bytes, then the memory is going to be on the order of 4 times the length of genome. So when we used the suffix tree, we had about 20 times the length of genome. Now maybe we're down to about 4 times the length of genome to store the suffix array. And that's better. In fact, the suffix array is hiding in the suffix tree that we were working with before. Remember, we labeled the nodes of the suffix tree with the starting position of the suffix that ended at that leaf. And if we do what's called an in-order traversal of the suffix tree, then we can reconstruct the suffix array by going down to 5. And then so we go sort of down and to the left as much as possible at each step. So we go down and to the left as much as we can, and we hit 5. Then 5's taken, so we go down and we go the next node over, so that's 3. Then we go down, and then we can't go to these 2 nodes, but we go here, and then we go left, so that gives us 1, and so on. So if we traverse the tree in this manner and go down to the leaves, then we're able to see this correspondence that the suffix array is hiding in the suffix tree. Okay, so then the question would be, now we have a data structure of Burroughs-Wheeler, which is about the length of genome. Now we have the suffix array, which is about 4 times the length of genome, maybe. And the question would be, can we get this down to approximately the length of genome? Can we shorten it even more, right? And that's what I hope Sean will be able to tell us about in the next section.